Hello everyone, welcome to the 8085 Microprocessor lecture series. This is lecture number 17. In the previous lecture, we saw some instructions, logic instructions rotate. So there are four rotate instructions, two rotate right and two rotate left. Now let us see some of the programs which are based on one of the program which is based on that rotate instruction. So here we have program 10 bytes of data are stored in memory location starting from 8040 to 8049. Write a program to find the negative numbers and store in memory location starting from 8050. So we have some negative numbers, some numbers which are maybe negative, which may be positive, from 8040 to 8049. There are 10 numbers. So we need to select the negative numbers and store in 8050. So first of all, what is the meaning of a negative number? So negative number, when we are using signed number notation, okay, in case of signed number notation, the leftmost bit, it represents the negative number, that the sign of the number. If the leftmost bit is 0, it represents a positive number, and if it is 1, it represents a negative number. Now in case of 8085, we have a data byte of 8 bits. Okay. So with 8 bits, we have this. Suppose if we are writing this 0 0 1 0 0 1 1 1. So this, if this is any number, so this bit, the first bit, this bit is actually the sign bit, and these are the this is the actual number. Okay. So 0 0 1 0 means it is 2, and 0 1 1 is 7. So this is actually plus 27. Similarly, if I write this as 1, okay, so it may leftmost bit, okay, in case of signed magnitude representation, if we write this as 1, and this is, suppose this is what we have, so this is 2, this is 7, and this is actually minus sign, so this becomes minus 27. So this leftmost bit, it represents the sign. Although if we observe, this number is actually A7. Okay, this is actually 1010 is A, and this is actually 7, so it is A7. In normal notation, normal hexadecimal notation, it is actually A7, but when we are using the sign representation, this is actually minus 27. So all the numbers, we can say, from 80 to FF, they, when we are using the sign representation, they will be negative numbers. Okay, so first we must know what is the meaning of a negative number. Next we will see the flowchart. This is the flowchart of the given program. So we start, then initialize the memory pointers. We need two memory pointers, okay, one for the source, other for the destination. Then we have to initialize the counter. Okay. Then we get the data byte and check whether it is positive or negative. If it is negative, then we need to store, yes, it is stored, and if it is no, then we must update the memory pointer, decrement the count. Is the counter 0? If the counter has become 0, we should stop. If it is not, then you must get the data byte and do the same thing again and again. Okay. Now let us see how do we write this particular program, the mnemonics of this particular program. Now let us see the program. So this is the mnemonics. So the very first instruction is LXI H8040. So we need to initialize the source pointer. So data is at 8040. Then LXID 8050, because we have to store the data at that particular location if it is negative. Then MVIC 0A, because there are 10 data bytes. So 0A means 10. After 9, 0A will come. Then what we do, we take the data of the very first data byte from the memory to register A. So move A comma M will ensure that the data which is at 8040, it gets transferred to A. Next, what we do is RAL. RAL means rotate accurate left through carry. So with this instruction, what will happen, with the data which is in A, it will rotate left. So when it rotates left, the leftmost bit, that is D7, it goes into the carry bit. So if that particular bit is set, that means the number is negative. If it is not set, then the number is positive. So we want to store the negative numbers. So after RAL, the leftmost bit will go into the carry. Now suppose here what we are checking is jump if. Suppose if carry is not generated. If carry is not generated, that means the number is positive and we are not interested in storing that number. So we just give JNC, jump if no carry. So 8010. So at 8010 of INXH, we get ready for the next byte 8 at 8041. Then DCRC, if to check whether the numbers are all the numbers are complete or not. So if it is not complete, so JNZ 8008. So now next move A comma M. So next data byte, let's 8041, will be stored in A. Again RAL. Now suppose let us assume now if carry is generated, then what will happen? If the carry is generated, there is no jump to 80410, but what it will do, we have to store again. This jump is not executed, so the next instruction will be executed. So move A comma M means what? Again we are storing from M to A. Now why do we need to store again? We are not directly storing the data of A to DE pointer, that is 8050, because in the whatever data we have in A, it has been rotated, so the data had been changed. So we need to get the original data again. So before storing the data, we have to get the data again. If we don't do this, then the rotated data will be stored. So therefore we again give this step, move A comma M, then STAXT. So STAXT will store the data of register A to DE pointer, which is 8050. Then INXD also comes inside this particular instruction after this. So INXD and then INXH. So this jump JNC will be executed, so that it goes to INXH. Okay, not INXD, it goes to INXH. So whenever negative number, whenever we get negative number, then only INXD gets executed. Okay, so this is the complete program. You can also execute it. Now with respect to storing, I will just show how to store. In the previous lecture I have shown how to store the data. So if this is memory location 8040, if it is 8041, suppose it is 8042, and so on. So we must store some data which is like suppose we can 10, which is less than 80, or we can store some data which is more than 80. So after storing this 10 numbers, we can run the program. So all the data bytes which are more than 80, they will be considered as negative. So they will come to this particular 8050. So the first one will come 82. This is not you won't get this because 10 is positive. So this way we can run the program and get the result. Now we will see some more logic instruction, that is compare. So we have CMPR, CMPM and CPI data. So let us see the first one, CMPR or CMPM. So this is a 1 byte instruction. It is used to compare the contents of register A with the contents of the specified register or the memory location which is pointed by HL register pair. Now there can be 3 cases. Let's see this in detail. So suppose if we have this, if we write like CMPB. So this CMPB, it compares the contents of register A with register B. Now of course 3 cases can arise if we are comparing the data of A with B. Now this can be any register, okay, B, C, D, E, H, L, any register. Okay, so when we compare this, 3 cases can arise. Maybe A is greater than B, or A is equal to B, or A is less than B. Now when we give this instruction, so which number is greater and which is smaller or both are equal, it is reflected by the flag, these 2 flags conditions, carry and 0 flag. They reflect the result. So if A is greater than B, then carry is reset, 0 is also reset. When A is equal to B, carry is reset but 0 is set. When A is less than B, carry is set, 0 is reset. So these are the conditions which are reflected These are the conditions. So from by checking the flag we can know, otherwise we won't be able to conclude which is greater than. So in order to know which is greater, what the result, we need to check this flag conditions. So how do we remember this? How to remember this? Like in for this particular case, we can imagine that we are doing a subtraction a minus b. So when we are doing a minus b, if a is greater than b, then carry is not generated, and there is no carry, no borrow, that is carry is acting as borrow, and zero flag is also not set. But when we are doing a minus b, and if a is equal to b, when a is equal to b, so the result is 0. So for that case, a is zero flag is set and carry is reset. And when we are doing a minus b, a is less than b, so carry, which is acting as a borrow, it is set and 0 is reset. So this is all what we get. Then next is Cmpm. Cmpm is of course similar to this, almost similar. Other difference is we are comparing the content of a memory location instead of this register B. So here Cmpm is also 1 byte instruction. It compares the contents of A with memory location which is pointed by HL register pair, and same thing, same conditions will get. This is what. Then we also have CPI 8-bit. So this CPI, the full form is compare immediate with 8-bit data. So this is a 2 byte instruction. It is used to compare the contents of register A with the given 8-bit data. Now suppose if we write this CPI 19H, so this particular instruction compares the contents of register A with data 19H. So it may happen that the data inside A is greater than 19H, or it may be equal to 19, or it may be less than 19. So with respect to that, this particular flags are set or reset. So these are the compare instructions. Now let us write a program based on the compare instruction. So we have program here. 10 bytes of data are stored in memory location starting from 8040 to 8049. Write a program to select the largest data byte and store in register D. So we have 10 data bytes starting from 8040 to 8049, and from this particular memory location we have to select the largest data byte. So let us see how we write the program. So here we have the program. The very first step is initializing the memory location. Now what strategy we are using in this case is we take the data from the memory location into A, because without A we cannot compare. So we take the first data byte in A and compare with the second one. So if the second data byte in the memory, if it is larger than A, we transfer that larger data byte in A and compare with the third memory location data. If the third memory location data is suppose smaller, then we don't interchange, we compare with the fourth one. So our strategy is that we always keep the larger data byte in A, and finally after executing the entire program, the largest data will be in register A and we transfer it into D. Let us see with one example. Suppose we have some data byte like here at 804, because we are starting from 8040. I will just take first three memory locations and it will be understood. So suppose here we have 05, and here we have 04, and here we have 07. So LXI-H, this instruction LXI-H 8040, so this is our memory pointer will be at this point. Okay, so we start with this memory pointer LXI-H, and MVIC 0A because we have 10 data bytes, so MVIC 0A, and then the first instruction move A comma M, so it transfers the contents of register M to it transfers the contents of memory location which is pointed by HL to A. So because of this particular instruction, A becomes 05. Now next we take INXH. So INXH, what happens with INXH is that our memory pointer now comes to 8041. This is our memory pointer now, new memory pointer. Now DCRC, we decrement this particular counter, so this 0A will become 09. Okay, and here we have JZ. So if this counter becomes 0, then it will directly jump to this second last instruction A to D and it will halt. so by that time A will contain the largest data byte, but since C is not 0, so this jump is not executed and we go to Cmpm. So Cmpm, it ensures that we are comparing the data in register A is compared with the data with this memory pointer which is 05. Now in this too, because A is larger, okay, so A is larger, so what happens is sorry, this is actually not 0, this is actually JC will come here, sorry, here we have JC. Okay, by the way, when we compare, Cmpm is done, so the data of A is compared with the memory pointer which is 04. Now carry will not be generated because A is greater, so JC, this instruction, this condition is not satisfied, so it will jump to triple star is here at this point. So next we have INXH. With INXH, the next memory pointer is 8042. Again DCRC, but because C was 9, now it becomes 8, so this instruction is not executed. Then CMPM. Now CMPM, now it will compare, because the new memory pointer is 8042, so these two are compared. Now here, because the memory is greater, the content of the memory is greater, so this particular instruction, this JC, so carry is generated and this condition is satisfied, so it jumps to double star is actually this point. So now this data M goes to A, so now A becomes 07. So this strategy is used for all the other memory pointer, and finally when the counter becomes 0, the largest data byte is in register A. So here I have written the mnemonics, the entire program with the mnemonics. Okay, this is the entire program with the mnemonics. Let us execute this on the Jubin simulator. So I have just entered the code. You can see these are the codes. Okay, opcodes have been entered up to 7, 6. So this is the last instruction. Now before executing the program, first we need to put some data in 8040. Okay, so that we must know which number is greater. So here I'll just make this at 8040 I'm storing suppose 1, then 8041 2, here 3, 4, 5, 6, 7, 8, 9, and at 8049 I store 10. So I know 10 is the largest data byte now. Now I am storing the data because I must know when after executing the program, I must know that 10 comes to A because 10 is the largest data byte. So after executing a program, 10 should be in A as well as register D. So now let us execute the program. So reset, go 8000 and then execute. Okay, the program is executed. Now again reset, register A, so register A contains 10. Okay, and let us see D, so D also contains 10. So this is how we execute the program. Now we'll see some common sources of errors while using the jump as well as some more instructions. So here the first thing is failure to clear register A when adding two numbers. So because addition cannot be done without register A, so when we are adding the numbers with A, if we want to add two numbers, we need to clear register A. Like in case of multiplication program, okay, we need to clear register A, otherwise what happens is the contents of A are also added if A contains some data. The next is a failure to keep a track of carry flag. So we have instructions where we can even clear and set the carry flag, so we must keep a track of that particular flag, whether the flag is set or reset before using those particular instructions. Then failure to update a memory pointer or a memory count or a counter. So when we are using any memory location operations involving some memory locations, so we must update the memory pointer. If we won't do that, then the same memory location will be used again and again, and if the counter is also not updated, maybe the program may run into infinite loop, so this must be taken care of. Then failure to set a flag before using any conditional jump instruction. So maybe we are using some conditional jump instruction, but like JNC or JC, but before that there is no instruction which could even set the carry flag, so it is of no use using that particular jump instruction. Then specifying a wrong memory address for the jump instruction. This is very common mistake when we are setting the jump instruction, we must ensure that we are setting the we are providing the proper memory address. Then finally, using improper combination of rotate instruction, so the whether we have to use rotate right, and whether rotate right through carry, and similarly rotate left, so rotate left simple or rotate left through carry. So these are some of the common sources of errors. Okay, we must take care of this. So that's all for this particular session. Thanks for watching.